Okay, welcome. Assignment 7, actually the deadline of assignment 7 is today, 22nd of March. And assignment 8 is next week, okay, next Friday. This is a longer assignment, so you should start soon. Actually, you should be able to finish all questions except maybe 1 or 2. But those questions you should be able to handle by the end of today. Okay, and then we have exercise classes this week. And last week, I was told the attendance was appalling. We have 1 student for the first slot, 4 students for the second slot, and then 0 student for the last slot. Okay, I see this as, I don't know, it's not a very good sign because I think we have video. The purpose of this video, in my opinion, is for you to revise. So we should try to synchronize with the class as much as possible. And now the session with 0 attendance, that is very bad because we are wasting the time of the TA. Okay, so I would like to see some improvement from this week. And I really want to see some improvement with the attendance of the class as well, right? Right now we are having only 15 students. That is very, not very ideal. And we have reading week next week, which means we won't see each other for 2 weeks. But be careful, reading week starts from Monday and it ends on Wednesday. Then on Thursday and Friday, we will have exercise classes. I plan to use these exercise classes to discuss midterm. And usually for midterm, the questions are confidential. So I do not want to distribute answer, and you should come to the exercise classes. There are 3 slots, and one of them will be suitable for you. Okay, I will also tell the TA in charge which questions I want to cover. I won't go through everything. The TA will, after I analyze your performance in the midterm, the TA will choose a few questions to discuss. So those are the weakest one in my opinion, okay? I have a quick look. It's not too bad, but not very satisfying either. So let's try to see what we can do to get through this course. Okay. Now, and then I have one question from Poon, and I would like to, I will check later, okay? I don't want to spend time on this right now. When can we get our scores back? Well, it depends on how fast I can finish marking. So I guarantee you, you will get it by the end of the last week. Okay, so that the final week is week 12, which is a bit shorter this term, this year. So let's say in the reading week, I will try to get through as much as possible. And well, okay, if you like, the reason or the excuse is I'm busy with other stuff. But I will try to create time to look at that. And I think I should be able to give you back, at least to give you the score. If you want to come and collect, you can, before the end of week 11. Okay? This is my service standard. So where is the calendar? That will be the 16th of April. Just give me a bit more time, okay? Do you, Poon, is it okay? To force myself to do it, I will, midterm score will be available by 16th of April. Maybe even earlier, with a bit of luck. Okay, but this is my promise. Okay, let's continue. This is a very fun part of the course. I really like it. I hope you enjoy all this partition function. Okay, I don't want to say too much, but I want to give you this picture. This is, by the way, from Blundell and Blundell, page 221. So this is the part, page 221 of Blundell and Blundell. This is the part where he discussed all these partition functions. And that is the point. Once we know how to write down the partition function, we can have a lot of stuff. We already tried that. And this is arguably the most important slide from last lecture. I do not want you to memorize everything, just like what you asked me before, what in the thermodynamic part, what do you need to memorize? What you should memorize is some way, the method to get all these equations. That is the more important part. And then a simple thing like this, you shouldn't memorize just the equation, you should memorize the meaning. Okay, now this one, of course, right now it's not familiar to you because you haven't seen why we get this n factorial, but soon you will see it. Okay, so this is last lecture, we talked about the difference between the single particle partition function and the system partition function. Okay, and then we show the relationship between the two. And we show that once you understand the relationship between these two different ways to look at the system, to look at your system, whether you want to look at it as the complete assembly or individual distinguishable particle, you have this relationship. And the end result will be the same because every time you see the single particle partition function, there's an n multiplying the log. And therefore, in the end, you get the same result. Okay, you want this, right? Otherwise, you have a problem, right? Depending on how you define your system, you get completely different answer. This is nonsense. We don't want that. Okay, but the point is, if you want to memorize only one equation, right? You want to choose this one or this one, memorize the one in blue because that will also be applicable when we talk about gas. Okay. All right, and then how did we test? We tested this machinery by plugging in the ingredient for a two-level system. We did it in two different ways. We did it by assuming a very general two-level system. And we put it in the form that we can discuss spin half very easily. Okay, and that is very satisfying because we learned how to write. We knew how to write the partition function, single particle partition function for the spin half system with two energy levels in the magnetic field, and we indeed get everything we want. We even got the Curie law. We got the form of entropy, which relates back to chapter 7 of thermodynamics. So we talk about adiabatic demagnetization. We got the heat capacity, which is something I told you we will be able to measure in the lab. Okay, so this is really a very nice thing to have. Okay, so today I'm going to look at a different extreme. That is the famous Einstein model. Okay, so why do we care about this? This is something that will be covered in solid state physics with a very different approach. Here we are going to, of course, use the machinery we developed, and hopefully, if some of you will be taking solid state physics, you will remember this treatment, or maybe you remember me because I told you this model before. Okay, so this is a famous system, and the model is like this. We assume we have We want to look at solid. So we have a bunch of atoms joined together by spring. Okay, you can draw the 3D case. But I'm not going to spend my life doing this. I'm going to draw a few more for you. Okay, this is our model of bonding. Right? How do we model the chemical bond? The physicist way of doing this is to assume there's a spring connecting the adjacent atoms. Okay, so Einstein model basically built on this. The assumption is you have an array of localized atoms, right? This is what we say a long time ago. If you have a solid, in principle, you know the address. So these are independent particles. So these independent particles feel the potential because you must have a potential for you to have this kind of equilibrium position. Okay, but this is a dynamic situation. Your atoms can vibrate. It can move. Okay, it can move around. And that is why this is a very good model to describe the vibration of atoms in a crystal. Okay, so maybe a few more. Okay, why is it fun for here? The reason this is fun for here is because you know how to solve it. You will be able to solve it. Because in quantum mechanics, you have a similar problem. But you don't do it like this. Maybe you do it by simply assuming some kind of harmonic potential, right? So you have spring. You have this kind of harmonic oscillator. So you know the energy spectrum. And here, by assuming each one of these will feel their own harmonic potential, we will have a bunch of independent harmonic oscillator, which we know how to write down the partition function. Okay, so this is very cool. And from quantum mechanics, you know the energy spectrum, En. Now this N is really integer. This is the quantum number characterizing the problem, not to be confused by the number of particles. Okay, you know this is the case. Okay, and this is indeed what Einstein assumed. He assumed all of these guys will have the same characteristic omega. Okay, I will say it first. This is what Einstein model assumes. So all simple harmonic oscillator are identical. And this turns out to be the assumption that breaks down later. But we are going to assume we don't know about that. Because this is just a preview. Now here, this is really the same omega for everybody. When you do solid state physics, you will see this omega has different dependence. You will have wave vector dependence, the wave vector Q dependence. Okay, and that is when you will have to revise this model and get a more accurate prediction. Okay, so our aim is to get heat capacity. Okay, so if you do it properly, that brings you the concept of phonon. It's the particle description of the lattice wave. Okay, so there, once you bring in the physics of phonon, you will have a different model which is called Debye's model. Okay, and my aim is to do a bit of Debye model, but not in the same level as the way we do it in solid state physics. We're going to just assume there's something called phonons, and then we are going to say, okay, these phonons are particles, and therefore we are going to use the appropriate statistics to treat these particles, and then get the heat capacity for you. So this is indeed part of my my goal to give you this, and this will be after the reading week. Okay, so right now, just assume we can treat this omega to be the same. Okay, that's why all simple harmonic oscillators are identical with the same angular frequency. Okay, and from here you see this is equally spaced, right? Your n can take n equals 0, n equal 1, n equal 2. And that will give you different energy. This is your energy spectrum. This is actually what I drew before. I drew it with epsilon 0 to be 0. But here, of course, you have the so-called 0 point energy. So your ground state will not be 0. Okay, this is famous problem. And I just take it from quantum mechanics. I'm not going to solve it for you. By the way, you have seen this, right? I hope. Should be in Professor Hui's course, right? Or even earlier. Okay, so this n, let me just write down what I need. So this n takes this number. This characterize the energy level, and this is not the particle number. Okay, so as usual, this kind of problem is very isotropic, which means if you know how to solve it in 1D, just imagine a chain. You know how to solve it for 3D. Okay, so let's do it for 1D, because mathematically, if you just look at the structure of the partition function, you know how to write down the solution for the 3-dimensional case immediately. So yes, let's start with the 1D case. Okay, what do? We input the ingredient. 1D means I only look at a chain. I only allow my particle to vibrate maybe along the x direction, say. Okay, so I have a chain, the particle can vibrate along the x direction, along the x-axis. So my single particle partition function, I'm going to just put 1D. I can put x, y, z, but the point is they are equivalent. That is the message I want to deliver. I can choose the other two orthogonal direction, and they will be the same form. Okay, this is an isotropic problem. Okay, what do? I just sum over all the exponential factor like before, right? This is the point of the partition function. Okay, well, let's just do that. Okay, we need to sum over all energy level divided by kBt. Okay, the first one, I will take n equals 0. So I have a half h bar omega. Okay, done. And the second one, now I use a single particle one. I'm not looking at the whole system. I'm just looking at one particle in its potential. Okay, the next one will be the 0 point energy plus 1n times h bar omega. Okay, and so on. Okay, this is a nice example where you have an infinite number of energy levels. This is very different from our 2-level system. Okay, but the good news is this is quite easy to solve. How do we do that? I'm going to pull out this common factor, right? This one. So I'm going to pull out this e to the minus a half h bar omega kBt. So the first term will be 1. And this is a sum here, right? So I can decouple it into the product. So I have minus h bar omega kBt. And the next term will be n equals 2. So I have a half, I have exponential minus 2 h bar omega kBt. And so on. Okay, what is this? This is e to the minus a half h bar omega kbt times sum over n. Now my n goes from 0 to infinity. I will have this e to the minus n h bar omega kbt. Okay, this is a geometric series, so you know how to sum them. This is geometric progression, geometric series, and therefore you know how to sum them, and therefore you know the answer. So this is minus h bar omega. I move this 2 to here. Now you know the structure. And this will be, this is really like 1 plus r squared plus r cubed, etc. Okay, so here, if you sum the geometric series, you have okay. And this is a result. I already get the partition function in 1D. And I can plug it into this machine. Not necessarily easy. If you are not careful, you can make mistake at many places. That will be, of course, a problem. But the principle is not difficult. Okay, so this is a 1D case. 1D case. But I want to compare really with experimental data. So this is this kind of 1D chain is hard to do. I want to really take a piece of solid, which is three-dimensional in nature, and calculate the heat capacity. Remember, my goal is to calculate the heat capacity. Okay, so now I need to write down the energy spectrum in 3D. So in 3D, I don't just have one n here, right? These 3 dimensions are independent. So I need to allow different n's. So my energy spectrum will depend on nx, ny, and nz. Okay? And you simply add this independent term, h bar omega plus ny okay, so these are the integers, so nx, ny, nz, they can run independently from 0 to infinity, independently. Okay. Now, why do I write this down? Why do we care about this? And the reason is this. I want this partition function. I don't want to plug this into the sausage machine. I want to do this. And if you want to do this, you need to sum over all kind of energies, right? So you have E to the energy divided by kBT with a minus sign. Okay, and once you take exponential, you will find that you can actually rewrite the sum into products. And these are 3 different 1D partition functions. Okay, it will be 1D. Okay, I will write X for you. Just one more step. Spy. Okay, right? So let me say this again. Once you recognize the form of the energies, you should be able to quickly recognize the way to write the partition function for the complete three-dimensional system in terms of the single particle partition functions in the X, Y, and Z directions. And these directions are equivalent, so I can call all of them 1D, like this. Okay, so I end up having this situation. Okay, so that is good. We have done the hard work. We just for the 3D case, we just plug in this and raise it to the power of 3. And that will do. Okay, I want to say a little bit more about this. The other thing I say in the note, I ask you to do it yourself, but because you are here, I'm going to tell you the answer. What did I ask you to do? I asked you to show that the internal energy for the isotropic case will be 3 times the internal energy of the 1D case. Okay, so this is something I want you to show. And then you will recognize that how do I get the heat capacity in the 3D case? I take the derivative with respect to temperature. And once I do that, I pull out this 3, right? So I will also get this result. Okay, to go from here to here, I take derivative with respect to temperature at constant volume. At constant volume. Okay, so now let's spend 1 minute. Tell me why this is the case in private chat. Why can I write this? The first line here. Why? Why? Okay, give me some answer. How do you see this? I want to see your way to see this problem. Once we sort this out, we are ready to move on. Okay, again, send me the answer in private. Why? How do you reach this conclusion? Thank you. Okay, I get 3 very different answers right now. One is very, very accurate. Okay, the other one come, which is good. Now, I want something very mathematical and simple maths. And the one that came last is correct, but with a question mark, which means the student is not very confident about the answer. More? You need to get used to this kind of argument, okay? Okay, the answer comes from the line before. Okay, why? How do you write the internal energy? You write the internal energy. In general, the internal energy has this form, right? Log Okay. Now, if you want 3D, you plug in the expression for 3D. And then you recognize that you have the form of the internal energy of 1D. And there's a power of 3 here, which you can pull out because of the log. Okay, so 1, 2, okay, 3. 3 students got it perfectly correct. Okay, congratulations. So this is the answer. This is what I asked you to think in the note, and the answer comes from here. This is the answer. Think in terms of this. Okay, so let's proceed. We already have this form, and we will be able to plug it in to calculate this. Okay, this is when you need to be very careful. The time to make very trivial mistake. Okay, now I will keep it here first and drag it up later. Okay, let's begin. I just need to calculate U1D. Then I would just multiply by 3 and get my answer. So U1D is n kBt square, partial derivative of log right? Which is this. So this is 1D case. Okay, so you have n kBt square. You take this expression and you take the log. So the first term will give you minus h bar omega 2 kBt. And then the second term, you take the log, you get log of 1 minus okay. There's a minus sign here, so I move it like this. Okay, and then you take the derivative with respect to temperature. Okay, and this is the part I don't want to do here because it's easy. It's easy to do it, but it's a bit messy. You can make silly mistake. So I will just write the final answer. Okay, now just trust me. Yeah. Okay, so this is the internal energy. And to get the heat capacity, here, heat capacity, we are going to take the derivative. So the CV of 1D, we are going to take the derivative. Again, right? So we already took derivative once. And it's a famous result that the 0 point energy doesn't contribute. So this term will be gone. And then you have this whole thing. And h bar omega Okay, so I will write you the final result, which is what I want to spend time to discuss. So the final result will be 3 nkbt, sorry, 3 nkb multiplied by h bar omega nkbt squared. And then you have this exponential of h bar omega kbt squared. Okay, now, so here there are some steps here. This is some steps missing, and then some step missing. But these are really not very difficult states, but can be messy. If you do it correctly, you get this result, and this is something we should discuss. How should we look at this? One way is to simply plot it. Remember what did I say last time? Last Wednesday, I told you if you have finite number of energy level, so if you have only two-state system, you get your heat capacity showing something like this kind of feature. And I argue that if you have infinite number of energy level, okay, this is only two energy level. This is a heat capacity. But if you have infinite number of infinite number of energy levels, you should not get something like this. You will see a heat capacity that grow and then saturate. Okay, this is what I say last time, and I told you the physics behind this. And now we want to see whether this function is compatible with this. So the way really is you take this formula and you plot it using Mathematica, your MATLAB, and this is the result. Okay, so let's have a look. So I'm going to need this 6. So I want to replace by this. Okay, so this is what I plot. I take this function. You see, I like to plot it in this form again. So I normalize to n kbt. Sorry, n times kb. And in the horizontal axis, I like to plot it as the ratio of energy scale, just like what I did with the spin. Okay, so here, this is the ratio. This characterizes the spacing between the adjacent levels, right? You have this n plus a half h bar omega. So h bar omega, you should imagine it as the spacing between the neighboring energy levels. This is again the same thinking process I would like you to have when we talk about the two-level system. Okay, and this this omega here, this omega is called the Einstein frequency. So this is the Einstein frequency. So what does it have to do with the physics of solid? So Einstein frequency, this is you can write it as omega E. Okay, if you don't like to use frequency unit and you insist of using temperature, there's something called the Einstein temperature. Okay, so if you Einstein temperature is theta E is simply h bar omega E divided by kb. Okay, if you write it in this form, then this ratio is equivalent to theta E divided by T. The whole thing will just collapse to this. You just compare two energy scales. If you prefer to use temperature so that you are able to imagine it better. Okay, and this energy scale characterize the oscillator strength. It tells you how strong your bond, chemical bond is. Okay, and remember this because I want to discuss a realistic example soon. Okay, another thing you should learn from this part is why do I plot it like this? I plot C heat capacity divided by 3 nkb. And I want you to pay attention on this number 1. Okay, when the heat capacity saturates, it doesn't saturate at a random number. It saturates at 3 nkb. So here, if you increase the temperature, I told you, you will not be able to absorb much more, right? The temperature keeps going up, but the heat capacity is flat. Okay, and what is the definition of heat capacity? Is the change of energy with respect to temperature. So what you are doing here is you simply just occupy higher and higher and higher level. Okay, but this gives you this saturation of 3 nkb. But this 3 nkb is the classical result. And the classical result is called Dulong-Petit law. Dulong-Petit law. Okay, which tells you if you approach the high temperature limit, high temperature, how do I define high temperature? High temperature when the temperature is much, much higher than the Einstein temperature, I will have this saturation. And you can see this happens around somewhere here, right? Greater than 1. So 1, this 1, why is this 1? 1 is when, in the language of Einstein temperature, this 1 means T is comparable to theta E, or the KBT is comparable to H bar omega E. Okay, so here it's not quite saturating yet, but if you go beyond that, you get saturation. Okay, and this is the classical Dulong-Petit result, which you can you might heard from chemistry or in other courses. And there, what do you hear? What you hear is the following. So the Dulong-Petit law, Dulong-Petit, basically say if I take a simple element, okay, simple element, at high temperature limit, high T limit, my heat capacity, my molar heat capacity will be around 25 joule per mole per Kelvin. Okay, now this is Dulong-Petit result, is a classical result. And what I did here, I did not tell you anything about any specific of the element. What I did was I wrote down the energy levels. I didn't even do it. I borrowed from quantum mechanics. I solved the problem by writing down the single particle partition function, plug it into this sausage machine, and I get my heat capacity here. And I plot it out for you, and I get this CV. This CV heat capacity will approach 3 nkb. I did it graphically, but you can do it analytically by looking at the high temperature result. Just massage this term a little bit. You are guaranteed to get this result. Okay, so this result looks very innocent. We just get all this knowledge we know, we integrate together, we get this result. And separately, you learn from other courses probably that the molar heat capacity of the simple element at high temperature, and for many elements, room temperature is considered high temperature. Okay, so if you Google, if you go to Wikipedia, you find the molar heat capacity for a lot of elements. You will find they are almost all clustered around this 25 joule per mole per Kelvin. This was remarkable. That's why it was given a law. Dulong and Petit saw that, observed that, and came up with this law. But now, what is the relationship between the two? Can we explain the Dulong Petit? If we can, then we have more. We should be happy, right? Because what we have done, purely from the mathematical treatment, can be applied to the real situation. Okay, let's spend some time to see that. Okay, this is exciting, right? Let's look at what this number is. So I told you CV3D is 3 nkb at high temperature, high T limit. Okay, I don't want to keep arguing about this anymore. You know what I meant by high T limit. High T limit means temperature is much greater than the characteristic temperature scale of the system, which is the Einstein temperature. Okay, how do I get this? I will show you now. So I want the molar, right? So I want this to be in terms of molar heat capacity. How do I get molar heat capacity? I need to look at one Avogadro number. Okay, so once I do that, the answer just drop out. So I have 3. Na times Kb is the gas constant, R. Gas constant is 8.3, so I indeed get about 25 joule per mole per Kelvin. So what I predicted here, you must be happy, because really it reduces back to Dulong-Petit law, which has been known for many decades, many centuries even. Okay, so now you might ask, then what is the point of doing all this if people already know the classical result? And in fact, you can argue that this is when scientists suspected something was wrong. Okay, what was wrong? If you look at the Dulong-Petit result, here, there is no temperature dependence. There is no way for you to put in a T artificially. There is no temperature dependence. Okay, the reason this was an important issue was the following. This is the heat capacity of diamond. This is heat capacity of diamond in a very obscure unit. This unit is difficult to work with, but that doesn't matter. Okay, something was wrong, because for diamond, okay, the argument is this. For diamond, room temperature is considered low for diamond. Okay, and therefore at room temperature, back then when people did this experiment, measure the heat capacity of diamond, they expect a saturation. They expected the Dulong-Petit law. But what they found was something changing. Okay, so actually I should have given you, let's see if I can read it from here. I should have given you the room temperature, but just bear in mind, at room temperature is not sufficiently high to see the saturation. So this is a bit like a bit of luck. You measure diamond, you expect the saturation, but you don't see the saturation. You see you are somewhere here in this part. And that is why you see the temperature dependence. And Einstein came in and tried to explain why diamond, the heat capacity would drop to 0 at low temperature. And this is when this kind of go pre-Schrodinger equation, but At that time, people already suspected that the classical physics is not the full story. So this contribute to this revolution, if you like. Okay, so let's complete the note. At room temperature, heat capacity shows T dependence. So this is against the Dulong-Petit result. Dulong-Petit law. Okay, and that is why, so need to answer the big question. So this need to answer why CV drops at low T, or why, even simpler than that, why CV the heat capacity acquires a temperature dependence. Okay, and that is when we have the Einstein model. But we should not just think Einstein was the only one who came to look at this problem. Debye also came in to solve this problem. Okay, so that's almost all I want to say. The final question is the following. I want to come back to the first line. Actually, two issues. I want to ask you why this is the case. Okay, give me some private message again. Why do you think in diamond, room temperature is not enough to reach the saturation? I think from your knowledge of your chemistry knowledge, I would say. Why are we so lucky? We take diamond and we manage to discover something is wrong using diamond. Any guess? Actually, some chemistry, some physics. Okay, nice. Diamond. Think about diamond. Why is diamond strong? There's another way to phrase this question. More? Okay, the answer, I think some of you got it. The answer is this. What do we compare? We want to compare this energy scale, H bar omega E. So if I want to see saturation, my KBT has to be much larger than H bar omega E. Okay? If this one is too large, comparable to the room temperature, of course, I will not be able to see the saturation. I will not be entering the classical regime where Dulong-Petit kicks in. Okay, so now your thinking process should go like this. What makes this omega E so big in diamond? Okay, so omega E, this is an oscillator. How do you write the oscillator? How do you write omega for an oscillator? Angular frequency of the oscillator. You write it like this. Okay, so if you have strong bond, this spring you use to model your chemical bond will be large. Okay, and that itself will boost omega. And another factor which turns out to play a role is for diamond, carbon is light compared with a lot of elements. If you look at the periodic table, it's really one of the lighter elements. So this boosts up omega. Okay, that is at least a hand-waving way to present this material to you. Okay, quite nice. I see a few nice answers coming. Okay, let's take a quick break. I didn't plan to spend too much time talking about this, but this is really exciting stuff. When I talk about this in solid state physics, I also talk a lot about this. Okay, so after the break, come back at 12:35. Let's move on. I want to begin to talk about gas, and that's another fascinating stuff. We are going to talk about indistinguishable particles, and I want to build some tools for you. And the tools will be density of states. Okay, so after the break, we are going to talk about this. Okay, see you again at 12:35. All right, so before the break, we talk about this Einstein model. I just look at my solid state physics textbook. I will give you this number and this should complete the treatment. So the Einstein temperature is 1320 Kelvin, right? So I already show you a way to compare that. So if you want to see saturation, your temperature has to be higher than this. For a lot of elements, if you just feed your data to the Einstein model, you extract an Einstein temperature of the order of several hundred Kelvin, say 100 Kelvin, 200 Kelvin. And therefore room temperature is kind of a good approximation for high temperature limit. Okay, so this is from Simon, Steve Simon's book. Simon's the Oxford solid state basic, solid state. Page 9. Okay, now one last question. Do you think this theory, this is the Einstein model, the theoretical curve is dashed line? The solid symbols are experimental data. What do you think about the agreement? Do you like it? Now, if you are very observant, you will see here it doesn't fit well. So this is where the second model comes in. Okay, so Einstein model goes down too quickly. If you work out the low temperature limit, you not the really the limiting case, or limiting case you get zero, nothing to play with. If you just look at the functional form at the low temperature limit, you will see an exponential behavior, which means the heat capacity goes down exponentially, which is too fast. Okay, and you see there are some lines lying above, and with the more modern data, this can be confirmed. So that is Debye's law. Debye can explain the low temperature behavior of the heat capacity, and that is called the Debye T-cube law. So that is to say the heat capacity goes down not exponentially but as power law, which is more realistic. And to get this power law, you will do the four-norm problem, and that will give you the power law. Okay. Next, this is another big chapter, another big story, and that is the story of indistinguishable particles. So what is the model? The model would be something like this. You take a jar, you take a container with a volume V, and your gas, you take some gas, and the gas is confined in this volume, in volume V. And how do you describe this problem? Okay, that is the goal for this chapter. Okay, how do we do that? This we will need something called the density of states. We will have first we need these energy levels, right? Just like the case of distinguishable particles, we need the energy levels of the problem, and then we want to put we need to associate some energies to the particles. Okay, here the energy levels will come from quantum mechanics, and they will be very, very closely they are closely spaced. Okay, which means you have a lot of energy levels and they are very close to each other. So in this case, and this is a clamp. You will see this soon. So for this problem, the energy levels will be closely spaced, and you will be able to see this soon. And therefore, we need a tool. The tool we need is called the density of states. And the reason we can do it this way is because we are going to treat these closely spaced energy levels as continuum. So you can treat these energy levels as continuum, rather than dealing with them individually as discrete level, right? This continuum has the advantage of simplifying the mathematics. Okay, so I want to start the problem from a dilute gas. I'm going to look at a problem where the gas is dilute, so we don't need to worry about the interaction between the gas particle. So we are going to start from the dilute gas. Dilute gas. This is this chapter. And next chapter, we are going to relax a little bit. We are going to look at the situation where you need to begin to worry about the concentration of the gas. Right now, let's for this chapter, we will start by looking at a case where we don't have to worry about the concentration of the gas. Okay, so what do we mean by concentration? What do I comparing? What I'm comparing is this. What I'm comparing is the number of energy levels with the concentration, with the number of gas particles. Okay, so here you will see that we will have a lot more energy states than the number of particles. Okay, and therefore you don't need to worry too much about two particles occupying the same energy level, because there are so many levels out there that they are not competing for the any particular energy level. But this is not the case when we talk about electrons in metal. There will be a gas which is called a Fermi gas, and this is not going to be the case when we talk about photon. There we also have a gas of photons, but there they can really get close to each other. And there we will be talking about the situation, the opposite situation. Okay. So let's look at how to solve this problem, and what kind of distribution, what kind of equilibrium distribution we can expect for such a situation. Okay, so I'm going to assume let's start from one particle. So let's say we only have one gas particle confined in this volume V. What is the energy spectrum? And this is the classic problem of the particle in a box. In a box of volume V. And this single particle is free. This single particle is free to explore a box with volume A times A times A. Okay, it's a box with the side A. And I'm going to set up my coordinate system such that the origin is at one corner of the box. So the origin is at one corner of this box. Now this is by choice, okay? I set it up this way. You can, now in the 1D equivalent is this. Why do I need to specify this? So this is my particle in a box for the 1D case. Okay, so I'm going to set the box to align like this. In 1D, I will have A on one side and 0 on one side. I could have done it differently. I can set the 0 anywhere I like. I can put it in the middle, but this is by choice. I put it like this. This would determine the form of the solution. So your wave function will be different. The description will be different. So if you do it like this, you know you have to put the node at the end. So if you do it this way, what function gives you this property? You get sines. Okay, if you put it in the middle, you will have cosine for this case, right? This is the ground state. Right? So this is a typical way to remember. I want to put the node at the end of the box because the particle cannot escape. This is infinite potential. Particle cannot escape, so the wave function must go to 0 at 0 and at A. Okay, so this is by choice. And in 3D, the box, this is in 1D. In 3D, the box will occupy 1 octant of your coordinate system. 1 octant. Okay, which means you can only have positive x, positive y, positive z. So you only have 1 octant. Okay, so if you set it up this way, your quantum mechanics, you solve the Schrodinger equation, and here a particle is free to explore the box. What do we mean by free? Free is it has real physical meaning. Free means I do not feel the force, and therefore there is no potential, and that is why I can draw it like this. So it's a particle in a box with a constant potential. Let's say a constant potential. So how do you write the force? The force is the gradient of the potential, negative gradient of the potential. So when the force, when the potential is flat, constant, you take the gradient, you get 0, no force. So particle is free. Okay, so you know from quantum mechanics, this is a particle in a box with only the kinetic term in the Hamiltonian. The potential term is constant, you can set it to 0. And the wave function in this case is a bunch of sine. I already justified to you that you get a sine for the x direction. Okay, and it's frequently written like this, kx times x, a. This will be can be determined by normalization, ky, and sine of kz times z. Okay, what is this k? So this kx is a wave number in 1D. So if you have kx, ky, kz forming a vector, this is called a wave vector k. Okay, now, and how do you write all this solution? You count how many half wavelength you can fit in. So the ground state will be, now this is a full wave, right? This lambda x is the wavelength. Okay, and you get half of this for the ground state. Okay, so you just take integer multiple of that. That's why you can write it like this. This is nx times divided by 2a. Okay, and this is your lambda x, right? So when I have 1, my lambda x is 2a, right? This is a, so the lambda is what I drawn here. It will be twice of that. Okay, and the next one up, I will just draw it like this. You always need to respect the fact that you have a node, so you will have like that. This has a lot of things to discuss, but I will just let you deal with this yourself. Okay, but you can see my nx, this nx runs from 1, 2, 3. Okay, nx equals 0 is not allowed when I set it up like this. I can set it up in a different way such that I allow nx to be 0, but this will have implication on the counting. Right? Let's just keep this in mind and keep all this possibility in mind. Right? So if I have ground state, my nx is 1. If I have the first excited state, my nx is 2. So I have, in that case, my lambda x is a, right? This is my lambda. You see, the wavelength is a. Okay, and similarly, I can write the rest. Okay, so similarly, I can write ky is ny times pi over a, and kz is nz times pi over a. Okay, this thing. And again, all this n must start from 1. Okay, we talk about this to be the situation where you have only the kinetic energy. So how do you write the momentum? The momentum px will be h bar times kx. So if you plug in the expression for kx, you will get nx times h times divided by 2a, not h bar, and so on. Okay. And what is p square? P square will be px square plus py square plus pz square. Okay, I can plug in my n. I will have nx square plus ny square plus nz square. Okay, and this will be is square, so I have to take h Planck constant divided by 4a squared. Okay, I'm going to call this n sub j. Okay, so now this is just really manipulating the symbols. So first I wrote down the wave function and justify to you how, what is the form of this case. And then from there we get the p, the momenta, in terms of this n, these quantum numbers, n's. Okay, what is the goal? The goal is to get the energy. So the energy spectrum is kinetic, so you get p squared divided by 2m, and that will be n. Now, I don't want to keep writing this, but this will be n. In a more condensed way, this will be n sub j square, h bar square, and then 8 times ma square. Okay, so I also don't want A now. I want volume. but I know a cube is my volume, so I will write it in terms of volume. Okay. Now, this is a standard way to do things. You can choose a box which is not a cube. That will make the problem more difficult. I'm serious. It's not like you just choose a random shape. You can solve it easily. But the point here is this: if you look at the physics of this problem, right? This gas, it doesn't really matter whether your box is a cube or a rectangle or a funny shape. And therefore, you should not expect the physics to depend on the shape of the box, but it should depend on the size of the box. And therefore, you can, as long as the volume is there, things will be okay. Okay, so this is true even if you don't have a cube. That's why I don't want this A anymore. I get it to, I change it to V. So let's label this. This is E sub J. Okay, but I write it like this, but remember the origin of this N sub J. This is really determined by this quantum numbers along 3 directions. Okay, so each one will define a state. Why do I write it this way? What I want to emphasize is this. Why do I do this? The reason I want to do this is you can have different ways to organize your nx, ny, nz to give you the same nj. This is degeneracy. This is a problem of degeneracy. So the energy depends on nj. But the energy state is defined by all 3 of them. I can have 1, 1, 0, which is a different state from 0, 1, 1. Right? 1, 1, 0, which is a different state from 0, 1, 1. But they will have the same energy. So this is the energy degeneracy. Okay, so what is next? From here, you know we will have a bunch of energy states by, well, if you like, writing down all these N's systematically. So far, we only consider one particle. If you want to discuss a huge number of particles, how do you do? You do the same, really. So now you have your particle in the box. You solve for the energy spectrum. If these particles are independent, the allowed energy is the same. Okay, so they will share the same energy spectrum. Okay, so where are we? Here. Okay, now after we have done all this groundwork, we can drop this J and think about how to describe this problem. So we are going to look at this scenario. Our energy is this one, H square, 8ma, nx square, ny square, and nz square. Okay, remember these are integers. So I'm going to give a picture. I think I have it here. So this is the picture I want to think about. Here. Okay, what is the scenario here? The scenario, this is in 2D, okay? It's hard to draw the 3D. This is a good picture. Now, if we think in terms of n domain, this is the n space. This is a space of n's, this integer. They are really drawn in integer. You see, this is, you are not allowed to take 0, right? So the first point here will be 1, 1. And x equals 1 and y equals 1. So this is 1 allowed. energy state. So each n, the energy state, let me say this again, the energy state is defined by your nx, ny, and nz. So in 2D, you get this kind of scenario. So each point here is a well-defined energy state. Okay, so we want to look at this picture and squeeze a few equations out. And more importantly, pay attention that I dropped this nj, but this nj will be large. This requires some number, crunching some number, but right now, just trust me. We are going to look at a situation where this sum will be some large number. And that will allow us to forget about the discreteness of this point and treat it as a continuum. Okay, why do I give you this picture? So this picture is relevant because I'm going to now look at this combination, right? Once I know how to deal with these three terms grouped in the bracket, I know how to deal with my energy because this is just a constant multiplier. Yeah. Okay, so the key is to understand more about this distribution of n's. So if they are large, I can draw something like this. So just use this as a reference. I can draw. I can define something as, let's say, r squared. Okay, this will carry the same meaning as nj, but why do I call it r? Okay, let me then rewrite it for you. Once I know how to calculate r, I say I know how to calculate e, right? Because this is related by 8ma squared divided by h squared times e. So this is just a very simple scaling between r squared and e. Okay, suppose you have a very large n. The question I want to ask is, how many states do you have below a certain energy E? Okay, suppose you know your energy, then you know your R. Okay, and I want to ask, how many energy states do you have that satisfy this requirement? Okay, how do you do that? So the question is this question: how many states? How many states are there with energy lower than E? How many? Okay, what is the trick here? Okay, listen carefully. If I ask you this question, this is equivalent to asking you how many states are there with energy lower than E or with R squared lower than some critical R squared. Okay, now if I'm looking at a large N, I'm looking at a very large circle or a quarter of the circle, an arc, right? So I can, what I really need to do is to calculate the area of this part, and then divided by the area per state. Then I can answer this question. Okay, do you get this point? Now let's look at this. Let's assume this is really in the unit of integer. Okay, so if I have some area like this, let me draw a different color like this. Okay, so this is 2 unit by 2 units. So this area in 2D, this is area. This area is 4 units. How many states do I have in these 4 units? The answer is 4 because you just count how many dots you have. I can count 1, 2, 3, 4. So I have exactly 4. Okay. So when I have a very huge radius, I can use the same trick. I just calculate the area divided by the number of units, the number of steps per unit area. I will get the unit, right? So this turns out to be 1 step per unit area. So this is why we set up the problem this way. You can set up the problem differently, such that this is not exactly 1, but some other numbers. Okay, so in 2D, this is what happens. In 3D, you have to talk about volume, and it will be the same logic. Okay, so answer. So the answer is this. The answer is, I'm going to call this, they are altogether n states, and this n state is related to this volume I talk about. Okay, this volume is the volume of the sphere divided by 8 because we are only talking about the positive quadrant. Okay, and you rearrange this. This is the answer. H squared. Okay, let me say this again. I ask for a threshold energy. Okay, so below the threshold energy, if I give you a threshold energy, there's a corresponding threshold radius. And below this energy, how many states do I have that satisfy this constraint? And that can be calculated by taking this R as the radius and calculate the 1/4 of the area of the circle in 2D, like this. Or in 3D, in 3D, it will be 1/8 of a sphere with the same radius R. So this is the volume divided by 8. That will be the number of dots enclosed by this volume, and that is the number of states satisfying the requirement with energy lower than some threshold energy. Okay, this is kind of important. This is a total number of energy, total number of states. Okay, and now I want to ask a different question. So the next question I want to ask is this. So the next question, a very typical question. I don't want to know the total number of states. What I want to ask is how many states. I want to know how many states between energy E and E plus dE. Okay, so I can define an energy. So in terms of the language of R, there will be some radius R. I want to know how many states do I have between R and R plus dR, which is this in this case of the 2D case, it will correspond to a very tiny shell between R and R plus dR. Okay, so there you, how many number, right? So you can do the derivative. This is, so the answer is D, you take dN, dE. Okay, and you take this expression and do it carefully, right? There's e raised to the power of 3 halves. When you do it, do this derivative, you get 2 pi a square, sorry, 2 pi a cube, h cube, 2n, square root of e. Okay, and this is the famous result. This is called the density of states in energy. Okay, this is the density of states in energy. How do you look at this? So if I write dn, that will be dn is g e dE, right? N is a number, is dimensionless. This is in energy unit. So this will have the unit of number per unit energy. Okay? So this is number per energy, and that is why people call it density. So my tips to you is you will see all kind of density of states. And always look at what is inside this bracket. What is the variable we are talking about? Another way to look at this is look at what is this differential that you multiply to get the unit of number. Okay, so this is density of states. This density is not the same as the density you are familiar with in like the mass density. Okay, it's not that. This is the number per unit energy. So that is why that is the meaning of density. Then you can have all kind of density of states. You can have density of states in a wave vector. Then there will be g of k. Okay, so this is the result, and you can do a lot of calculation with this expression. Okay, we develop it here, and we are going to use it again and again. For example, when we talk about electrons in metal, we are going to take the density of states, but that is not enough. For electrons, you have spin, you need to account for additional degeneracy, and therefore you need to multiply by 2 here. Okay, so but basically this G of E, usually I like to write it like this, GEDE. I always like to remind myself what this is, what is the meaning of this. Because look, if you integrate, suppose you integrate from 0 to infinity, you must be able to account for all the states. Okay, and that is the meaning of this n. You must recover your n. Okay, so this is really counting in the energy space. Okay, so let's write this and box it. I write this DE for you. Okay, next I want to put in a few numbers to justify a few things I say up to now. Okay, what did I say? I told you we are working on the situation where we have a lot of energy levels compared with the number of particles. So let's consider this scenario. Okay, so if we look at a volume of gas at standard temperature and pressure condition, STP condition, and let's take a typical box of 10 centimeter. What we want to ask is how many states do we have? So this we need to choose some gas to talk about. Let's choose helium. So I'm going to choose helium. So this is 6.64 times 10 to the minus 27 kilogram. Okay, we need the Planck constant, but that you know. And standard temperature and pressure. So my energy is of the order of kBT. Okay, I'm going to look at this scenario. And room temperature will be about 25 milli-electron volt, something we should remember. Kb times T for room temperature is 25 milli-electron volt. And that is equivalent to 4.0 times 10 to the minus 21 joule. Okay, the first thing is we need to estimate what is the equivalent R square, this radius of the sphere I talk about. Okay, so that expression I had is this. Okay, if I give you a threshold energy, you will have a threshold R. Okay, and this you really just take your calculator and practice it and have some feeling about this. You get a number, right? This is dimensionless because this is related to the sum of nx square, ny square, and nz square. So these are numbers. Okay, so you know, in this case, your R will be about 2.2 times 10 to the 9. You take the square root. Okay, now we are ready to answer this question. How many states do we have? How many states? How many energy states? This is the number of energy states given by N, right? If I give you this threshold energy, you get the threshold R. You plug it in, you know how many states are below this threshold energy. And those are the states that you are in principle allowed to occupy. And plug in the number, you get 5.5 times 10 to the 27. Maybe not too meaningful to you right now, but just know that this is a huge number. I drew you this picture. This is really not accurate because we should have a lot more dots, a lot more dots. Okay, so in other words, we are talking about a very huge R for a typical statistical mechanics problem here. Okay, and now how many particles? This is another question. How many particles? How many helium atoms? How many? Okay, now this requires some chemistry. We know our volume is A cube. Is you know the A, you know A cube. This is 1 liter. Okay, and you know 1 mole of gas at STP occupy 22.4 liters. Okay, now you work out the ratio. I have how many mole here if I have 1 liter? Okay, and this X is the number of mole. So the total number of atoms will be how many moles I have multiplied by Na. Right, so from here I have my X mole, this is in mole, and multiplied by this Avogadro's number, and in the end the result is 2.69 times 10 to the 22. Okay, please check all this. But this is what I want to say now. So now you work out the number of states, which I claim is much larger than the number of particles. Okay, and you take this number, this one, and this one, and you will find that this is now this is 27, this is 22. You get something of the order of 10 to the 5, like this. Okay, now I hope you appreciate that this is a huge number. How do you imagine this? Now the way to imagine this is this. Imagine the population of Hong Kong. So we have about 7 million people in Hong Kong. If you work out this ratio, these 7 million people are sharing 35 cars. So this is how dilute the number of cars we have. Okay, so this ratio will give you this. So this justifies my claim from the beginning that we are looking at a situation where we have a lot of states compared with the number of particles. That is important because there will be some approximation, a very good approximation that we can make to make progress about this gas, to talk about this gas problem. Okay, I think I need to stop here. So that's all for today, and next lecture we will begin to introduce a concept called a bundle. We have all these energy states. How do we deal with this? We are going to cut it into bundles and then learn how to distribute particles within the bundle. Then we look at the entire system again and discuss the equilibrium distribution. Okay, so this is what I present today will be very relevant for Wednesday's lecture. So Wednesday, I think we need to push a little bit faster to achieve enough for the reading week. Okay, thank you very much, and I will see you on Wednesday.